Welcome back to Applied Mathematics. In this video, we're going to be factoring binomials. This video is going to focus, as we have in factoring, on building up the algebra skill, our eye on the prize of getting to bigger algebraic structures that we can apply this to and use those to solve problems in everyday life and in industrial applications. If by chance any math teacher stumbles across this video in YouTube and you have a great way of livening up the lesson on factoring binomials with applications, I would love to hear about it. I have been searching for years and I've come up empty-handed. To my students, I apologize. I have been searching for years and I'm coming up empty-handed. The rules for factoring binomials, I guess I should have gotten in on this first, right? A binomial, nomial sounds like a polynomial, bi like a bicycle that has two wheels. A binomial is a two-term polynomial. A classic binomial might be something like a squared minus b squared. This particular arrangement of terms is called a conjugate pair. A conjugate pair is a very fancy sounding way of saying you are subtracting two things, and those two things are linked in some interesting way. In this case, the interesting way is that they are both perfect squares. All right, so this is a conjugate pair difference of squares. And the rule here is very simply that whenever you have a squared minus b squared, it's going to factor and become a plus b times a minus b. You can figure this out by going through and turning this into a squared plus 0ab minus b squared and factoring it like a trinomial. But that is a lot of effort and it's very annoying. So memorizing this formula is probably your best bet. I hate telling you to memorize things, but it's probably your best bet. So if I have something like x squared minus 9, I recognize that 9 is 3 squared, and I know that this is going to factor to x plus 3 times x minus 3. That's all there is to it. If I have something that's a little bit more complicated, 4x squared minus 81. Well, 4 is a perfect square. 4 is 2 squared, so 4x squared is 2x, the whole thing squared. And 81 is 9 squared. So this is going to factor to 2x plus 9 times 2x minus 9. One of the really fascinating things with the difference of squares formula is that it becomes applicable when you have higher powers, and it can do some very interesting things. I kind of like that 81. We'll stick with that, but instead of 4x squared, let's take a look at x to the fourth. Because x to the fourth is x squared squared. So this factors to x squared plus 9 times x squared minus 9. And wait a second, we just factored x squared minus 9. That factors to x plus 3 times x minus 3. One of the most important things about factoring binomials, or the rules for factoring binomials, is that very often when you factor something, you end up with a binomial. And sometimes that binomial can itself be factored. Also related to that, example I wanted to go through here. How about 7x cubed minus 7x? This is a binomial. Neither 7x cubed nor 7x is itself a perfect square. So this is not the difference of squares. But there are common factors. There is a common factor of 7, and there's a common factor of x. And when I factor that out, I'm left with x squared minus 1. And x squared minus 1 is the difference of two perfect squares. Clearly, x squared is x squared. And you don't often think about it, but 1 is 1 squared. So that factors out and becomes 7x times x plus 1 times x minus 1. I do want to stress that this formula relies on the fact that it is subtraction between the perfect squares. The sum of squares, a squared plus b squared, cannot be factored. That's why if you go back to this example, that side that ended up x squared plus 9 just stayed x squared plus 9. There's nothing else you can do with that. If you have, instead of perfect squares, perfect cubes, then sum or difference are both perfectly valid. A cubed plus b cubed, a cubed minus b cubed. And honestly, this is an opportunity to introduce the plus or minus notation and its conventions here. When you have a cubed plus or minus b cubed, it is going to factor to a plus or minus b times a squared minus or plus ab plus b squared. The first oddity that I want to stress in this formula is this plus or minus, minus or plus. The idea here is that I don't want to have to write out two separate formulas. And whether it is plus or it is minus, it follows a very similar scheme. So if I follow the top branch, then I have a cubed plus b cubed, then I have a plus b, and I have a squared. The top branch now says minus ab plus b squared. Or if I follow the bottom branch, a cubed minus b cubed equals a minus b times a squared. The bottom branch over here is plus ab plus b squared. You can write out both of those rules separately. It is perfectly fine. They do both work. But I wanted to introduce you to this plus or minus convention because that is something that you see very frequently in writing out formulas. The other thing that I wanted to point out here is that the sum and difference of cubes rule ends up with this extra term. Our rule for factoring trinomials will never allow you to factor this further. That's not quite the same thing as saying that the polynomial cannot be factored. If it turns out that a itself has an x squared in it, then sometimes this thing can be factored, but we're not going to develop the tools in this course in order to do it. We're just going to hope that that never comes up. Instead, let's dive into a quick example. How about x cubed minus 8? Clearly, x cubed is x cubed, and then 8 is 2 cubed. And so we're going to use the difference of cubes rule, which tells me that this is going to factor to x minus 2 times x squared plus x times 2, which we normally write as 2x, plus 2 squared. Well, 2 squared is 4. If I have 27x cubed plus 64, well, 27x cubed is 3x, the whole thing cubed. 64 is 4 cubed. How do I know this? Oh, off to the side, where you can't see it, I wrote down the list of all of the perfect squares and perfect cubes. Well, not all of them, but a couple of them. I literally just grabbed my calculator. I wrote the number 1. I plugged 1 squared into my calculator, I wrote 1. I plugged 1 cubed into my calculator, I wrote 1. I wrote the number 2. I calculated 2 squared, which is 4. I calculated 2 cubed, which was 8. 3, 9, 27, 4, 16, 64, 5, 25, 125, and continuing from there. That way I can quickly look at my list and determine, do I have a perfect square? Do I have a perfect cube? If so, maybe one of these formulas will work. If I don't, then I move on with my life. Anyway, I now have this written as the sum of perfect cubes. I can use my sum of perfect cubes formula. It is going to be a, 3x, plus b, 4, times a squared. 3x, the whole thing squared, is 9 times x squared, minus a times b. 3x times 4 is 12x, and then plus b squared. 4 squared is 16. I don't know of any way of deriving these formulas for the sum and difference of perfect cubes. As far as I've been able to tell, mathematicians developed these formulas because bored mathematicians in the 1500s and 1600s were just writing out these calculations and seeing what happened, and they stumbled across a couple of things that turned out to be interesting. I suggest having these formulas at ready reference in front of you so that you can look at them and you can use them when appropriate. But that's really all it is. It's a couple of formulas that you need to know and you need to know how to use. Right. That's all I have for you in this video, so I'll wrap up with that. As always, thanks for joining me. See you next time.